The universe is composed of the system and the surroundings. The system is the small, well-defined part of the universe in which we are interested. The surroundings is defined as everything that is not the system. Enthalpy is a thermodynamic state function that is often used in thermochemistry and has the symbol capital H. Unfortunately, we cannot measure the absolute enthalpy of a system. However, we can clearly measure the change in enthalpy, delta H. Delta H is equivalent to the heat transferred from the system to the surroundings or vice versa. And so delta H equals QP, the heat at constant pressure. As I mentioned before, capital H is the enthalpy and delta H is the change in enthalpy, where the delta sign symbols the change. The subscripts after the delta sign, R, C, or F, represent the type of process being considered. For example, R for reaction, C for combustion, and F for formation. The subscript after the H indicates the temperature at which the change is measured or reported. And the superscript not here, or 0, represents the standard pressure, which is 1 bar. In an exothermic process, heat is transferred from the system to the surroundings, and therefore, according to our convention, delta H of the system and the heat at constant pressure is negative. By contrast, for an endothermic process, heat is transferred from the surroundings to the system, and so according to our convention, delta H for the system and QP is positive. In this example, we are asked to determine the sign of delta H and state whether the reaction is exothermic or endothermic. In question A, we see that heat appears on the product side of the reaction, and therefore heat is released, and therefore delta H is negative, and the reaction is exothermic. In question B, we see that heat appears on the reactant side of the reaction, and therefore heat is absorbed in this reaction, and so delta H is positive, and the reaction is endothermic. Stoichiometry can also be applied to thermochemistry. A thermochemical equation is a balanced reaction that includes delta H. Now, although delta H is strictly speaking an extensive property and should be expressed in kilojoules, when written as part of a reaction, it is usually expressed in kilojoules per mole of reaction. The sign of delta H indicates whether the reaction is exothermic or endothermic. When delta H is negative, the reaction is exothermic. When delta H is positive, the reaction is endothermic. The magnitude of delta H, when written in kilojoules, is proportional to the amount of substance, and as mentioned previously, this is because delta H is an extensive property. Finally, the value of delta H can be used in a calculation in the same way as mole ratios. So we can easily convert between the amount of substance given in moles and the enthalpy, or delta H, in kilojoules that is absorbed or released in a reaction. The major source of aluminum is bauxite, which is a mineral known as aluminum oxide, which has the chemical formula Al2O3. Its thermal decomposition can be represented by the reaction shown here. Al2O3 decomposes to 2Al plus 3 halves O2. Delta HR for the reaction, or the change in enthalpy of reaction, is 1,676 kilojoules per mole. In this example, we are asked to calculate the number of grams of aluminum that can be formed when 1.000 times 10 to the 3 kilojoules of heat is transferred. So the strategy for solving this question is to start from the amount of heat transferred and use that to calculate the number of moles of aluminum, which will be calculated from delta HR. Once we know the number of moles of aluminum, we can calculate the mass of aluminum using the molar mass. So again, the strategy is to start from the heat transferred and use that to calculate the number of moles of aluminum and then calculate the mass of aluminum. So starting with the amount of heat transferred, which is 1.000 times 10 to the 3 kilojoules, we divide by delta HR, which is 1,676 kilojoules per mole of reaction. Now here we're interested in aluminum, and we notice that in this reaction, there are 2 moles of aluminum that are produced. So in this case, we would divide by 1,676 kilojoules per 2 moles of aluminum. Okay? In doing so, we see that the kilojoules cancel, leaving us with moles of aluminum, which is what we wanted to calculate. Lastly, we can use this to calculate the mass from by multiplying by the molar mass, which is 26.98 grams per mole. And we'll see here that the moles cancel, leaving us with the mass of aluminum in grams, which is what we want. Multiplying that in our calculator gives us 32.1957 grams. And since each of our data points has 4 significant figures, our final answer should have 4 significant figures. So we would round to 32.20 grams of aluminum as our final answer.